All right, everyone, welcome back to another deep dive.
Uh,
Today we are going to be tackling a really interesting paper on multi-objective optimization.
I'm excited about this one.
Yeah, I know you are, and it's actually a listener request. One of our dedicated deep divers sent this paper in and asked for the plain English explanation. So
Love it.
that's our mission today. The title of the paper is Multi-Objective Regionalized Bayesian Optimization via Entropy Search.
Oh, yeah, that's a mouthful.
It is a mouthful. So let's break that down a little bit. Let's start with multi-objective optimization. I was trying to think of a good analogy for this.
Yeah, it's kind of it's a tough one to explain sometimes.
It is. It is. And I was thinking, it's like you're trying to plan a party
Right.
and you're trying to figure out, what kind of pizza to order.
Yeah,
But everyone has different preferences, right?
right.
Some people want meat. Some people want veggies. Some people want extra cheese. And you're trying to find, the best possible pizza that's going to satisfy everybody.
Sure.
But there isn't really one best pizza, right?
You got it.
It's more like a set of optimal solutions.
That's right. And that's actually a concept known as the Pareto optimal set, which we might get into
There
later.
you go. So that's multi-objective optimization, right?
Yeah.
It's like finding the best solutions when you're juggling all these different and sometimes conflicting
Absolutely.
goals.
Yeah.
And then you've got this term Bayesian optimization. So
Yeah.
how do we bring that into the mix?
Well, Bayesian optimization, it's kind of like if we stick with the pizza analogy, it's like you're not going to just bake a pizza with every single topping combination.
Right.
And try them all, right? Because that would be a waste of time and ingredients.
Yeah, you'd be eating pizza for weeks.
That's exactly right. So instead you're going to use the information from the pizzas you've already tried to kind of guide your next choices.
Right.
So, if you know that people generally like pepperoni, you're probably going to include pepperoni on the next pizza you bake. But you might also try adding something new, right? To see if you can discover a new winning combination.
Okay, so it's kind of like you're building on your past experiences to make more informed decisions.
Right.
And that's where this new algorithm comes in, MORBS, multi-objective, regionalized Bayesian optimization via entropy search.
Catchy name.
Very catchy. So what makes this algorithm special?
Well, what's fascinating about MORBS is that it uses this concept called entropy to kind of guide its search. And entropy is basically a measure of uncertainty, right?
Yeah.
So think of it like this. You go to a buffet, right? And there's all these different dishes.
Yeah.
And you don't know which one's going to be the tastiest, right? So you kind of have to sample different things.
Right.
And you're probably going to focus on the areas of the buffet that seem to have the most potential, right? So, maybe you'll see a dish that looks really interesting, or you'll smell something delicious coming from a certain part of the buffet.
Right.
And you're going to be drawn to those areas because they have more uncertainty or higher entropy.
Yeah.
Right? And that's kind of what MORBS does.
So it's not just randomly picking solutions, it's strategically targeting the ones that have the most potential.
Absolutely.
For exciting discoveries.
That's it. And, in the paper, they also talk about these trust regions and this technique called Chebyshev scalarization. Sounds really complicated, but
yeah, unpack those for us.
Yeah. So, imagine dividing that buffet into different sections, right?
Okay.
Each representing a different type of cuisine, right? So you've got your Italian section, you've got your Asian section, and so on. And MORBS is basically going to select the center of each of these sections, these trust regions, using entropy as its guide, right? And then it uses Chebyshev scalarization to find the best dish within that region.
Okay, so it's like it's dividing the problem into smaller chunks. Exactly.
And then tackling each chunk strategically.
Yeah. And, Chebyshev's function, you can think of that as a tool that helps minimize the worst case scenario.
Okay.
In each region, right? So make sure that no matter what you choose, you're not going to end up with something completely terrible.
Right. Gotcha. So it's like a safety net.
Yeah.
In a way.
Right.
Okay. So this all sounds very sophisticated.
Yeah.
But how does this compare to traditional methods?
Well, traditional methods might kind of stick to the well-trodden paths, right? They might just optimize within the areas that are already known to be pretty good, right?
Okay.
But MORBS, with its entropy-driven approach, it actually dares to venture off the beaten path and explore those less crowded regions where it might stumble upon some hidden gems that others miss.
So it's like choosing the scenic route.
Exactly.
Instead of just sticking to the highway.
You got it.
Okay. But how can we be sure that MORBS is actually better at finding these optimal solutions? Like,
Right.
how do we know that it's actually working? Well, they actually put it to the test.
They did.
Yeah, they ran a bunch of experiments to see how it performed. Yeah, and they tested it on a variety of problems, like some theoretical ones and some real-world problems.
Okay.
They used something called synthetic benchmark problems.
Oh.
So, like the DTLZ test suite, which are kind of like standardized problems
Okay.
that researchers use to test out different algorithms.
Okay. So kind of like a testing ground.
Exactly. Yeah.
Yeah.
And they also tested it on some really interesting real-world problems, like designing a welded beam
Okay.
and planning the trajectory of a Mars rover.
Wait, a Mars rover. So
Yeah.
this algorithm could actually help us explore other planets.
That's right. Yeah, it's pretty cool stuff.
Wow, that's amazing. Okay, so how do they actually measure how well this algorithm performs? Like,
Right.
how do we know if it's doing a good job?
So they use this metric called hypervolume.
Hypervolume.
Hypervolume, yeah. And think of it like this. Imagine you're comparing different travel itineraries, right? And a higher hypervolume means that the itinerary covers a wider range of experiences. Like it hits diverse points of interest without sacrificing too much time or budget.
Got it.
So it's kind of a way to quantify how effectively an algorithm balances those competing objectives.
So it's not just about finding a solution.
Right.
It's about finding a diverse set of good solutions,
Exactly.
each offering like a different balance.
Yeah.
Like, I'm starting to see why this hypervolume thing is so important.
Yeah, it's a key metric in this field.
Yeah.
And when they compared MORBS to other methods, it actually did really well.
Really?
Yeah, it often came out on top. It achieved higher hypervolume scores, and it also converged faster.
Converge faster.
Yeah.
What does that mean?
So converging faster basically means that the algorithm finds those optimal solutions more quickly.
Okay, and why is that important?
Well, it's crucial in real-world applications, right?
Okay.
Where you have limited time and computational resources.
Right, like with our Mars rover example.
Yeah. Exactly, like you want to find the most efficient path as quickly as possible so the rover can spend more time exploring and gathering data.
Yeah, that makes sense. Okay, I'm following you so far, but I gotta admit, when I was looking at the paper,
Yeah.
there was a lot of math involved.
It can get a little bit technical.
Especially when they were describing how MORBS uses this entropy concept.
Right.
They even had an equation for calculating something called information gain.
Yeah, yeah.
What is that all about?
So, don't let the equations intimidate you.
Yeah.
The key takeaway here is that MORBS is using entropy, which is that measure of uncertainty,
Right.
to strategically guide its search.
Okay.
It's like a detective looking for clues,
Right.
right? The areas with the highest entropy are the ones that are most likely to yield new information.
So it's not just exploring randomly.
Right.
It's using like information theory to maximize.
Yeah, it's being smart about it.
Okay, that's pretty clever. But let's step back from the technical details for a second. I'm curious, what are some real-world scenarios where this could be applied, like, beyond designing robots and planning space missions?
We think about personal finance, for example. You're trying to maximize returns while minimizing risk.
Right.
Or imagine planning a trip with friends. You've got different preferences and budgets to consider.
Yeah.
Multi-objective optimization, with its ability to balance all those competing goals, could help you create a travel plan that satisfies everyone.
Okay.
Or an investment portfolio that balances your financial goals and risk tolerance.
I see what you mean. It's not about finding a single best solution.
Right.
It's about providing a range of options, each representing a different trade-off.
Yeah,
That could be incredibly helpful in those situations where there's no one-size-fits-all answer.
absolutely.
Okay, but the researchers didn't just stop at testing MORBS, did they?
No, they didn't.
What did they highlight as its key advantages?
Well, they highlight a few key things.
Yeah.
First, as we already talked about, it converges faster in a lot of their tests.
Right. Like in our Mars rover example, every minute counts.
Exactly. And it's not just about speed, though.
Okay, what else?
It's about how well it balances exploration and exploitation.
Okay, remind me what that means again.
Sure. So it's not just about exploiting what we already know,
Okay.
but also venturing into uncharted territory to see if we can find even better solutions.
Right, so like instead of always going to your favorite restaurant, you try a new one.
Exactly. You never know what culinary delights you might discover.
And they found that it did achieve higher hypervolume scores, right?
Yes. Definitely higher hypervolume compared to other methods.
So instead of giving you one best solution,
Right.
it's giving you like a menu of options.
Exactly. It's giving you a range of possibilities, and you can choose what works best for you.
Okay, that makes a lot of sense. So many different areas where this could be applied.
Oh, absolutely.
Think about like designing a personalized fitness plan.
Yeah.
You're trying to balance intensity and duration and recovery time.
Yeah.
Mormis could help you create a plan that maximizes your results without, burning out or getting injured.
Absolutely. And think about designing a sustainable city.
Wow.
Balancing energy efficiency and affordability and quality of life.
So many possibilities.
Endless possibilities.
This has been an incredible deep dive. We started with this research paper about an algorithm.
Yeah.
And we ended up talking about optimizing everything.
It's amazing how these concepts can apply to so many different areas.
Yeah, it really shows how powerful these ideas are and how they can impact our lives.
It all comes back to balancing multiple objectives.
Finding solutions that really work in these complex situations.
Absolutely.
Well, I want to thank our listener for sending in this paper.
Yeah, great paper.
And sparking this conversation.
It's been fun.
It has been fun. And to all of our deep divers out there, keep those curious minds engaged.
Stay curious.
And remember, sometimes the best discoveries are in those less explored corners of the map.
That's right.
Until next time, happy optimizing.